Thank you so much for coming to Stanford to participate in STAT's 385 Theories of Deep Learning. We're really honored and pleased to have you here. You've come from Switzerland, and we really appreciate that. So, as the first question, can you tell us about yourself and your current research activities?
Right, should we take the mic or? No? Oh, okay, good. So first of all, thank you very much for having me. It's a pleasure and an honor. And thank you for your hospitality. So I'm currently working on deep learning, but that's not the only thing I'm doing. I'm also working on Shannon theory in general, compression, analog compression, and using tools from geometric measure theory that we brought into this field, trying to understand how well you can compress analog sources. Then we have activities on unsupervised learning, subspace clustering, still on wireless communications, interference channels, trying to understand the nature of interference and coming up with mathematical tools to study interference channels. And surprisingly, there's this beautiful theory of fractals that plays an important role in interference channels. And along the way, you have this very fragile theory of very special structures, and in the end, you get very, I think, practically relevant statements. So that's something that I really like, that you walk the path with these very fine, fragile tools, and in the end, you get very robust statements. So these are more or less the things I'm currently working on.
Nice. Can you also tell the audience maybe your current position, where you're coming from, and where you're a professor at?
All right, sure. So I'm a professor at ETH Zurich, the Swiss Federal Institute of Zurich, in the Department of Information Technology and Electrical Engineering. And I've been there for 15 years now. And before that, I was at Stanford for 2 years and 1 year at UIUC.
Thanks, Helmut. So, because this is about deep learning, so I'm going to ask you this question: that what do you think that theory and, in general, theorists can contribute to deep learning?
Well, I think fundamentally, scientists are trying to understand, and I think a theory of deep learning is an attempt to develop an understanding of the tremendous success that these tools have had in practice. And having said that, I think it's important to have many different theories, just to look at things from different angles. And I also am convinced that eventually, these practical successes, I think they will reach a point where theory will be needed to move them further. And I think it's important to start early with that.
Okay, great. So as my last question, before I pass the microphone on to other instructors, I want to give you a topic, and you tell me up to 3 words about that topic. Jeff Hinton.
A descendant of George Bush.
Great. So 3 words only.
Oh, sorry.
So that's a rule.
All right, good.
Zermatt.
Matterhorn.
And the last topic, Helmut Boltzke.
Now you caught me off guard. Appreciates beauty.
Great. Thank you so much. So I'm going to pass it on to Professor Bauer.
So I'd like to just explore what you think about theory as it relates to deep learning, as what a good theory might be like, what it might deliver, what practitioners might learn from it. We've spoken a bit over lunch about some of these topics, so you've had a little bit of time to reflect. So what might a successful theory of deep learning be like? How will we know when we're seeing a successful theory of deep learning?
So I think I like to look at this from two different angles. One is the non-utilitarian, but you were mostly interested in the utilitarian. On the non-utilitarian side, I think it should be beautiful mathematics. On the utilitarian side, what I think is remarkable about deep learning is that it does so well for so many different applications. It almost seems to be like the universal computational tool that we have always been looking for. So I think a successful theory should bring out the universality aspect of deep learning. I don't think it's as important to bring out the minimalistic, canonical, computational elements of the theory, because we have a lot of compute power to deal with that. And finally, I think it should lead the way towards this grand theory of unsupervised learning, because I think right now, and then I guess I'm paraphrasing Jeff Hinton, I think children don't need millions of images of cats to recognize a cat. So I think that's what he's saying, and I think that's the next big step to try to understand unsupervised learning. So if a theory of deep learning could deliver that, I would consider it successful.
Okay. There are at the moment a number of authors with theoretical papers about deep learning, and as you know, in this course we're going to hear from several of them. You, of course, are the first in the series, and we've been very impressed by your work. I wonder if you've had a chance to study any of the other work that we might be covering, or if there's some particular theoretical work by someone else that maybe we're not considering but that's been impressive to you or interesting, or that poses a particularly fruitful way of looking at things.
So first of all, I think the more theories, the better. I think that's how things work in science. You have to have different perspectives, and I think it's good if more people get interested in theory. It also brings new talent into the field, and I don't think at this point, or maybe for that matter ever, it's so important to pick a winner of these series. They may all help us to shed light on very different angles. So I said the universality aspect, some of the series bring them out, some don't, but they bring out other things. So I think it's good, and I think it creates momentum and opens possibilities for people with mathematical backgrounds. So now clearly I do follow closely what my colleagues are doing, and I'm very impressed by the activity, and I think there is a number of papers that I have benefited from greatly, older papers or papers maybe that are not so much in the limelight now of theories of deep learning. And so I think the paper that I want to mention here is Tom Cover's 1964 or 65 paper on linear separability and nonlinear separability of dichotomies. So that's a paper that I've personally benefited from greatly. That helped me to understand basic problems of learning theory and nonlinear mappings, etc. And I have perused quite a bit Mashkar's papers with Caltech for this part or the second theory that I'm not presenting today on approximation theory. So we have benefited greatly from his papers. Some of them have been impressive. And then certainly the work I'm presenting today significantly builds on Stéphane Malat's work and was a great inspiration that we drew from his work on scattering networks based on wavelets. So that's something that I have profited and benefited a lot from.
So one more question which I'm personally interested in. It feels to me that people of a theoretical bent are mostly uber skeptical about deep learning. And then there's a small group of people, of whom you're very prominent, who've embraced it and are really interested in it. So there's something that got you to go from being a skeptic or a rejectionist to being enthusiastic and interested. If you had to say something to a person of theoretical bent who's currently a skeptic about why they may want to embrace this and learn more about it, what would you say?
So personally, I've not gone from being a skeptic to embracing it. That's not how I view science. I think it's a great opportunity if you have something that works remarkably well. I mean, for I think engineers all their life have been trying to understand things, and I think this is understanding I would view it as a fabulous machine that delivers so far unseen things, and I think the very nature of a scientist should be to try to go and take the machine apart and understand what's in it and deconstruct it. So personally, I got interested in the field because of one of my former PhD students, who is now at Rice University, went to a plenary talk by Jeff Hinton and came back and was all excited about deep learning, and I had looked at some of the papers before, and then I said to the student, I'm going to look at this in more detail, and my student tried to dissuade me. He said, there's so many people doing these things and working in deep learning, are you sure? And the more he tried to dissuade me, the more interested I got. And then I had this new PhD student who said, I don't care what my research topic is, it has to do with harmonic analysis. So I said, okay, let's do harmonic analysis of deep nets, and that was about 4 years ago. I'm going to talk about that today. So what would I tell mathematicians that are skeptical of, or mathematically theoretically inclined people skeptical of deep learning? I do think that's not how we should, as I said, view science. I think that's how life works. Sometimes things are built from first principles and then later implemented and brought to practice. That was the case with many things, for example, in wireless technology, where the theory was developed on paper and then was put into chips, and we have been using it very successfully. But sometimes practice proceeds very fast and theory has to follow, and I think that's the case here now. And I do think that we have almost an obligation to try to understand why these things work so well, and put the tools that we know to use. And that was the attitude that I took. So I try not to be judgmental and just look at these things. And I think the first litmus test that I apply is, do I think that some beautiful mathematics could be done? And it's a very non-utilitarian view. And then I decide whether to go into a field or not.
Thank you very much. Gordon?
Okay, so the first question is, in your opinion, what is the single most important question, theoretical question in deep learning that needs to be answered?
I think good fields hardly ever have single most important questions to answer. But if I were forced to pick one, let's say, aspect of deep learning, then I think it's the universality aspect of deep learning, and I think that's what singles deep learning out from many other techniques.
So if we could clarify, when you say universality, are you referring to, for example, the transfer learning aspect, that something that can be learned from one set of images could then be used in a completely unrelated set of images? Or could you delineate a bit if that's not what you're thinking about?
What I was thinking about is that we have essentially, let's say, one structure. I mean, there's different network structures, but one concept: convolutional networks, nonlinearities, many layers, deep networks that have been exceedingly successful in many different applications. ImageNet contest, MNIST, handwritten digits, but now we see it being applied in chemistry, we see it applied in particle physics, we see it applied in finance and so on. So all these problems, you would think, have very different structural components beneath them, and yet this one single tool, deep learning, does so well. The transferability aspect was not really what I was thinking about, and I have to say I haven't thought about this much, but I think that there's one tool that you can apply universally, and I think that for me makes it stand out.
Second question is a bit provocative. If you could revive any mathematician to work on deep learning and perhaps help you, who would you choose?
That would be John von Neumann.
Okay, and out of those who are currently present?
Charles Pfefferman.
Thank you. Do you think that you have to extend the boundaries of mathematics in order to explain the success of deep learning? Or do you think that previous tools that were developed to date are sufficient?
So first of all, I think if deep learning helps to develop new mathematics, that's most welcome, and I think that would be great. Is it needed to explain the success of deep learning? Fundamentally, a deep neural network is a nonlinear transformation of an input signal to a feature vector, and we're trying to understand the specifics of this nonlinear transformation. Now, having said that, I know it's a somewhat simplistic view, but fundamentally that's what it is. I think if you compare nonlinear operator theory to linear operator theory, clearly linear operator theory is much more developed and much more is known, or linear systems are much better studied than nonlinear systems. So, but there is a lot of mathematics on nonlinear systems, nonlinear dynamical systems and so on. So I think these are the areas of mathematics that may be brought into deep learning, and quite frankly I don't know these areas in enough detail to say whether new tools will be needed or not, and I think it's very hard to say at this point, but I would certainly hope it sparks new mathematical developments. But I think the bottom line is it's a nonlinear transformation, can be a nonlinear dynamical system, and this is the framework that we should probably look at it, and that doesn't include generalizability, so there is of course a statistical component. Yeah, very hard to say at this point, but I think we have lots of work ahead of us using the tools that are around.
Thank you.
Hi everybody. I just want to make some quick announcement about the course and today's question and answer. So if you're taking this course, you know that there is a Canvas website for the course, and there is a question and answer section. If you go to discussion section of your Canvas, either on your mobile phone or on your laptop, there is a thread that says question and answer with Helmut lcskei. And if you have any questions during the talk, please post your questions over there, and then we'll curate them and ask Helmut at the end of the talk.
We're intending a 20-minute question and answer at the end of the talk, so don't everybody just leave right away. We would like to get some classroom engagement here.
Yeah, that's the announcement I had for today. And then some people ask, is there any special format for the review paper that we asked for the grades? It's just like any other academic review that you would write for a paper. That would be it. But we really appreciate your contribution to the discussions. So please get on Canvas and post your questions, and don't be shy. Some people, they contacted me. They're like, "Oh, nobody posted," or "My question is like this. Should I post?" Yeah, you can post anything that you want on Canvas, and then we will curate them. Okay. So today we are honored to have Helmut lcskei. He is coming from a long way. He's coming from Zurich. He accepted our invitation, and we are happy to have him here. He's going to talk about harmonic analysis of deep convolutional neural networks. Floor is yours.
Okay. Thank you, Hatef. Good afternoon, everybody. Welcome. I'm Delighted to be here. I would like to thank David, Hotef, and Verdun for perfect, extraordinary organization. Everything was super smooth, perfect service, and also for the nice poster that you put together. That I sent a formal picture, and they wanted some cooler pictures, so I thought, let me send some climbing pictures, and this is what they did. So thank you very much. I'm going to talk about joint work with my former PhD student Thomas Wiatowski, who just graduated, and Philip Gross, who is a mathematician at the University of Vienna. He's an approximation theorist. Now, deep neural networks, so I'm sure you know there's different theories that are being developed right now, so I'm going to try to show you some of the results that we have obtained in the last couple of years with that have a harmonic analysis flavor. The ImageNet contest, 1 million images, 1,000 categories, classifying images into different categories. You know that over the past couple of years, deep convolutional neural networks have consistently won that contest, and they're also outperforming now the best humans in classification error rates. A second application of deep neural networks is image annotation, or describing the content of an image. And there are papers that describe the tremendous successes, practical successes. So here's a picture, and I would like to ask you to annotate the picture to describe its content. Anybody want to start with the first name of the gentleman? Yeah, that comes at some point. There is a conducting, yes, very good. Stick, no. Let's start. So, Carlos, any? No. Kleiber. If you don't know him, I highly recommend listening to his recordings. Needless to say, one of my favorite, if not favorite, conductor. Conducting the which orchestra? Yes, of course. Thank you, Andrea. Had to be. What else? Which concert? What do you think? Which concert? Any ideas? What is the best known concert at the Vienna Philharmonic? New Year's concert. And now this is for the aficionados. Carlos Kleiber conducted it twice. 1989. Okay, the other one was 1992. You know, in the life of a conductor, being selected to conduct the Vienna Philharmonic for the New Year's concert is like winning a Nobel Prize or something. And there are some that won it 5 times, like Daniel Barenboim, for example, or Zubin Mehta, and so on. And Kleiber did it twice. By the way, this is totally made up. That paper here has a picture of a stove with 2 pizzas on it, but I didn't find this aesthetically pleasing, so I just reassembled things here. Okay, good. Let's get into things. Now, fundamentally, what neural networks do is they take an input signal and apply a nonlinear transformation. And that is called nonlinear feature extraction. So they map an input F, this is an image of Claude Shannon or John von Neumann, map it to a feature vector, and then they apply a linear classifier and then decide when it's positive it's Shannon, when it's less than 0 it's von Neumann. So what I want to focus on in this talk is I want to try to understand this nonlinear mapping and try to use tools from harmonic analysis that are traditionally tools that have been used mostly in linear problems, but you will see that they turn out useful also when you have nonlinearities involved. Now, why nonlinear transformation? So let's suppose you have a dichotomy. You have 2 sets of points, the blue ones and the red ones, and they live on circles of different radii. One is less than 1 and the other one is greater than 1. And if you wanted to separate these 2 sets of points using a linear classifier, obviously that's not possible. So what you would do is you would look at this and you would say, well, I know I have 2 sets of points that live on circles of different radii, so I just want to put a circle in the middle, and then I want to separate the points, and I just look at what is inside the circle and what is outside. And more technically speaking, you could apply a nonlinear transformation. So you just take the magnitude of the points, and you have a feature extractor that has the magnitude magnitude and a 1, and then you take a weight vector with a +1 and a -1, and then you get essentially to decide whether the radius was greater than 1 or was less than 1. So that's red or blue here. Another way of thinking about this, obviously that's a nonlinear transformation. Another way of thinking about this is that you look at your classification problem, you have certain invariances that you want. For example, you don't want your classifier to be susceptible to the phase information. You want to ignore the phase information because all you care about is the radius. So this we call an invariant. You want the feature extractor to be invariant to the phase. Now that leads us to this problem of, or this theme of invariances in deep neural networks. The way I like to look at them is that they help you specify the nonlinear transformation. You read a lot about invariances, by the way also covariances, and I will talk about it later. But they essentially help you, if you have some prior information, specify the feature extractor. So if you look at the MNIST database, so that's a very famous one, and you want to classify those handwritten digits, if I give you those 3 pictures of the number 3, you will immediately say, well, each of them shows the number 3, and you don't care about the absolute position of the digit 3 in the picture. So you would like your feature extractor to be invariant to the spatial location, and that leads to translation invariance, one of the main themes in deep neural networks. Now, having said that, whenever you want to be invariant to translations, you know, if translations are involved, the step to convolutions is not far, but you would say, well, wait a moment, convolutions are actually not invariant at all to translations, they are fully covariant. So if you take an LTI system, you apply a translation at the input, you get the same translation at the output. So you don't absorb the translation, you actually just pass it on to the output. So why would we want to use convolutional kernels in deep neural networks? Well, it turns out that if you pair convolutions with pooling, then you can actually get networks that have in the first few layers translation covariance, and the deeper you go into the network, the more invariance you get. And this is something that people have observed in practice, and you will see actually that can be proved. And more on that later. The second thing is you want to have a feature vector that, let's say, has certain robustness to certain nonlinear transformations. So for example, this is a picture of which mountain? Matterhorn, obviously. Probably the most depicted mountain on the planet. Now if you fly Swiss Air, they have in the new 777, they have pictures of the Matterhorn in the cabin, in the main cabin. They are gray, white and black, so they are not very intrusive, but still you get to see the Matterhorn for 12 hours on your flight from Zurich to San Francisco. So afterwards you know every single corner of the Matterhorn. So here is you know, somebody on his way back from the Matterhorn and is still in good shape and holds the camera steady, and this is somebody who has exhausted himself on the mountain or herself, and the camera is shaking. But in both cases you recognize the Matterhorn, so you want certain insensitivity to small acquisition jitters or to different resolutions. So these are translation variants and this insensitivity to certain nonlinear transformations. These are the 2 main themes that I want to focus on in this talk. And what I would like to do is I would like to discuss this network structure that was originally introduced by Stéphane Mallat in 2012 and called scattering networks. And we extended that, and I will talk more about that later. So let me describe the structure for you, and then let me tell you why many of the architectures that you find in the DNN literature fit into this framework. The picture is a little bit intimidating, but really there is not very much to it. So you have an input signal F. You filter it with a set of filters, the G lambda 1 through P through G lambda 1 of K, just a convolution, and then you apply a nonlinearity. I just put the modulus here, but it doesn't have to be the modulus. So in Mallat's work, these filters here are scaled versions of a Matter wavelet, so it's a wavelet transform, and the nonlinearity is indeed a modulus, but in a more general architecture, these nonlinearities can be any Lipschitz nonlinearity, okay? And also the filters can be any filters, and that's important because in practice you often want to learn those filters, or you even find papers where people use random filters. That's one of the interesting things with deep neural networks. You get exceedingly good performance with totally random filters. You just draw realizations of random processes, to take those realizations as convolutional kernels, and you get fantastic performance if your network is deep enough. So all this is contained, Lipschitz nonlinearities and general filters, and then you filter, you apply the nonlinearity, and then you branch out here and you filter, apply the nonlinearity, and so on and so forth. And so it's a tree structure. But what you do is, these are the so-called feature maps, then you extract those feature maps into a feature vector, and you do that by filtering this quantity here. In my last work with a low-pass filter, in the general architecture with a general filter, and those red circles, they contain the signals that go into the feature vector. Okay, so first filtering, nonlinearity, filtering again, and that you put in the feature vector. So you have an input f, you map it onto a phi of f, and the elements of phi of f are the elements in this red circle. Needless to say that the dimensionality actually increases very fast with network depths. And what is interesting, and that's the first result I want to show you, is that this network architecture per se, no matter more or less what filters you use, what nonlinearities you use, and also what pooling operators you use. So you can choose any Lipschitz nonlinearity, you can choose average pooling, you can choose pooling by subsampling. Again, you know, there has to be some Lipschitz property. The filters have to satisfy some mild condition. But more or less, independently of what you do at the node level, the architecture per se guarantees that you have translation variance and small deformation sensitivity. And then you can fiddle around in those nodes and, as I said, do whatever you want, and it's going to work out. Talking about translation variance, or talking about nonlinearity, I showed you before that nonlinear mappings, they have certain invariances. So if you talk about translation variance, can we get translation variance through a linear transformation? Well, if you think about it, so I'm going to try to write on the board here. If you have a linear transformation, A times X, and you want translation variance, that means that you don't want the output to depend on whether you shifted the input or not. So let's suppose you apply the shift operator to X. So let's suppose we call the shift operator D. So we look at A dx, we look at A d squared x, and so on, and A d to the nx. So we apply all shifts. You know, there's an n by n matrix here, so we have n different shifts, and we would like all these quantities to be equal to each other. So that means what we want is having said that, that means that since this has to be satisfied for all vectors x, that we need A d to the L to be equal to A. Now if you do that, if you apply the shift operator from the right, you see that you're cyclically shifting through the columns, and that means if you do that n times, that means all the cyclically shifted versions of this matrix should be equal to each other. That means you have a rank 1 matrix, so the one column you repeat it n times, and that's it. So now what's the problem with having this kind of matrix? It has a null space of dimension n minus 1, so you're going to throw away most of your signal because it has this non-trivial null space. Okay, so nonlinear is required. Linear is not going to work. What is the simplest nonlinear transformation that you can think of that is going to give you full translation invariance? Well, what happens if you take the Fourier transform of the shifted version of a signal? Well, you get the phase factor in the frequency domain, then you take the magnitude and you're done, right? So if you have f times x and the magnitude, then this is invariant to translations. Okay, the magnitude just takes care of the translation. Now we could say, well, we are done here. Well, what is the issue with this here? Well, the Fourier transform is a very global transformation. It just looks at the entire signal and it doesn't give you local information. In feature extraction, often we're interested in local information. Okay, so that explains why there should be some nonlinearity. And of course also because of the invariance that we want. Now, the filters, the building blocks. I told you that the filters are pretty general. The filters here are they form a semi-discrete frame. So I don't want to go into lots of technical details on frame theory, but essentially the way you can think of this is the following. Just think of R2, a basic orthogonal base is 1, 0, 0, 1, and then you have a general basis that could be just two vectors that are not collinear. And then if you have more than two vectors, then you form a redundant system. It's called a frame. And this double inequality here is called the frame inequality. What is unconventional is that this is a semi-discrete frame. So you have a set of filters, you have a set of convolutions, and what you get is for each filter, you get a continuum of frame coefficients. So if you think of the convolution, you convolve x of t with some g of t minus tau, then you can think of this as taking the inner product of x with g, let's call it minus, and we have, we flip this. So with a flipped and shifted version of g. So you take a g, you flip it, you shift it by t, and y of t for each t is a frame coefficient. So you get a continuum of frame coefficients, and that you do for each of those filters. So you have a discretely, or countably, I mean in this case it's countably, indexed set of filters, and each filter produces a continuum of frame coefficients, and that's why this is called semi-discrete frame theory. Discrete frame theory is the standard frame theory as it's most widely used, and then there is a fully continuous frame theory. For example, the short-term Fourier transform is a fully continuous frame expansion. It's a concept that comes from theoretical physics, and there's papers by Antoine and Ali in the early 1990s on continuous frame decomposition. So that's where you can find these things. So this is here essentially saying that you take all these frame coefficients and you take their energy, and I extracted this one filter here. I will talk about that later, but this is part of the frame. So the g lambda n and xi n, they all belong to one set of functions, and you want to have completeness. It's a completeness condition, and you want the operator, the frame operator, to be bounded. Now you look at this and you say, well, how difficult is it to find filters that satisfy this here? Any guesses? Do you think this is really difficult to find filters that satisfy this condition? It looks like it would be, but since I'm asking, it probably isn't. But do you think you can just sit down and just come up with a set of filters that satisfies this? You can actually very easily do this. All you do is you take this double inequality here, and you apply a principle that is called unitary equivalence. So you map the frame operator into the frequency domain, and what you then get is this condition here. All you need is that the sum over all n, and then the g lambda n plus this one filter that we extracted satisfies this double inequality here. So this is what is called a Littlewood-Paley representation of the frame operator. So for the communication theorists, you know this as the Nyquist condition when we don't have a continuous frame. When you sample, then you have the Nyquist condition where you just have this here, and then n divided by some t or whatever. And usually this has to be constant. That's a Nyquist condition. That's a tight frame condition. This is just a relaxation of the Nyquist condition, and it's for the continuous case. So the bottom line is just make sure that these filters don't have common zeros, and you're going to be fine. Okay? So it's a fairly mild condition. So that's for the filters, and we're going to use that throughout. And why do we want completeness? Well, I said before that we don't want to lose information in the network. So eventually this feature extractor is a nonlinear transformation. We want to make sure that we have a trivial null space, and I will show you later what happens if you don't have a trivial null space, because all the points that end up in the null space of the operator become unclassifiable, no matter what your separating vector W is going to be. But that is not going to guarantee yet that your feature extractor is going to be a trivial null space, because you have nonlinearities involved and so on. If it were just linear, no nonlinearities, then having a frame in every layer would make sure that you have completeness throughout, but that's it's not as simple. Okay, so the filters that satisfy these conditions are a wide class of structured filters, wavelets, well, Heisenberg filters, ridgelets, shearlets, alpha shearlets, whatever, learned filters. I mean, you have to be really unlucky to get filters with shared zeros. I mean, it's virtually not going to happen in practice. Nonlinearities, I said this before, they have to be pointwise and Lipschitz continuous, so the magnitude, of course, works. It's satisfied by virtually all nonlinearities that are used in the deep learning literature, the ReLU, rectified linear unit, the modulus, the logistic sigmoid, and so on. So the Lipschitz property is not something that you wouldn't find satisfied in practice. Pooling. What does pooling do? So you have the output of your nonlinearity, and then you try to pool, you aggregate information. Why do you do that in practice? Well, I showed you this tree structure. You see that dimensionality is actually increasing very quickly with a number of layers. So typically people pool in practice in order to reduce the dimensionality of the feature vector, because you don't want to feed feature vectors of dimensions trillions into your support vector machine. So that is one reason for doing pooling. Another one, as you will see shortly, is to get translation invariance. So the pooling operators we look at, they are of this form here. We emulate discrete time pooling in continuous time. So you have a Lipschitz operator, Pn, and that I'm going to show you, that could be just if you do pooling by subsampling, this is just identity, and then you just do subsampling but in continuous time. Or if you do pooling by averaging, then you have an averaging kernel here, and you subsample the output. So you just average, take local averages, and you just output a local average. Okay, so you collating a number of samples and just representing them through one sample. So that's pooling. And again, the theory applies as long as you have a Lipschitz continuous pooling operator here and subsampling. So that's something, it's a little bit of, because you have to emulate discrete time pooling. To be careful. So the first result, vertical translation variance. Remember what I told you is that the network structure I showed you, essentially irrespectively of the filters, and now you understand what I mean by irrespectively. It means as long as they satisfy the frame condition, which we convinced ourselves is not overly hard to satisfy, as long as the nonlinearities are Lipschitz, as long as the pooling operators are Lipschitz, you get this result here that compares the feature vector up to the nth layer. So remember, we had this tree architecture, and then we extract the features corresponding to the vector f, and compares them to the features corresponding to a translate of that vector f. And so you would like this error. So the triple norm, by the way, is the feature vector is a vector where each element is again a function. So you take the L2 norm, and then over all the L2 norm you take the little L2 norm. So that's the triple norm here. It behaves like this. So it depends, of course, on the magnitude of the translation, but also depends on the pooling factors. So what you see here is that if S1 is the pooling factor in the first layer and Sn in the nth layer, if you choose them to be larger than 1, just slightly so, and if you do that for every layer, and if you let the number of layers go to infinity, then this error is going to go to 0. But more fundamentally, what happens is that we are not only interested in the asymptotic result, but this shows why, as you go deeper into the network, the features become more and more translation invariant. And that's something that actually practitioners have observed. Having said that, the features on the first few layers are going to be covariant. I mean, what happens if you have a convolution? And you shift the input, you shift the output. So if you don't do pooling, if you choose all your SIs to be equal to 1, you're not going to get any translation variance in the network. The features are going to be fully translation covariant. Now that's not necessarily a bad thing, but often you want translation variance, so then you can accomplish that through pooling. But there are applications like facial landmark detection where you would be interested in having features that are translation covariant. And so my thinking is that the first few layers, the features will be mostly translation covariant, and the deeper you go into the network, there will be more translation invariant. And then your support vector machine, your linear classifier, your weight vector may want to put more weight on the first few layers if you're interested in covariance, and it's going to put more weight on the layers further down if you're interested in invariance. Okay, so it's not that we are just blindly going after invariance, so both are present in the network. But if you don't do pooling, you don't get invariance. Okay, so that's easily, yes?
So, but this bound doesn't take into account the example that you gave before. If you do Fourier and then absolute value, then even without pooling, you will have translation invariance.
Exactly, right, yes.
But this doesn't show up in this.
Yes, but that's global, and here there's locality, and I'm going to talk about that shortly. And also there's this issue of the null space and so on. So there's more. But I'll come to the locality issue in a second. Good. There's just some normalization condition. I think it's not worthwhile really mentioning this. So this applies to general filters, general nonlinearities, and general poolings. So what I want to do next is I want to talk a little bit about the philosophy behind invariance results, and I want to compare them to Stefan Malat's work, which was a great source of inspiration for us and was one of the reasons why we started being interested in deep neural networks. So if you remember, I told you in Malat's work, he looks at wavelet transforms. So each of the filters is a scaled version of a prototype filter of a mother wavelet, and the magnitude. And what he gets is what we call, so this term is actually our term, he doesn't call it horizontal, we call it horizontal translation variance. In his case, he lets the number of wavelet scales go to infinity, essentially making this into a continuous wavelet transform, and then he gets translation variance on every layer. Okay, we don't get that. What we get is translation variance, increasing translation variance as you go deeper into the network. So that's why horizontal. On every layer he gets it, but the number of wavelet scales has to go to infinity. And here it's a vertical translation variance result. Good, I think I said all that. Next, nonlinear deformations. So the deformations that we want to look at here are deformations that Malat also looked at. So this is f tau of f. So tau is a function. We look at deformations of the form f of x minus tau of x. And so the idea is that this kind of deformation would model, for example, in the MNIST problem, different handwriting styles. Of course, that's a bit of a stretch. I mean, does it really, and so on. But you get the idea. You look at this figure 5, and you see, okay, these are different handwriting styles, and you can actually look at what this nonlinearity does, and you can mimic these kinds of things. So that's more or less what happens here. Obviously, there are limits to this. I mean, if you're too large, if your tau is too large in a certain sense, I mean, you can turn any number into any other number. So you have to impose limits on how large this tau can be in a certain sense. And you will see later what I mean by how we measure the size of tau. Now I want to talk a bit about the philosophy behind this deformation in sensitivity results. So ideally, you would like to have, for all functions f and L2, you would like to have little sensitivity to these deformations here, because obviously you want to recognize this as a digit of 5 no matter what the handwriting style. So you don't want your feature vector to depend too much on this tau of x here. And as I said, you would want to do that for all L2 functions. Now let's see if that question is a meaningful question. Well, if you take tau of x to be the Gaussian function, for example, and you take a function that is more or less smooth, and you see what this does is, I mean, if your x is further away from the origin, you hardly have any shift here, and you have some action here around the origin. So for this smooth signal, you make a dent here around the origin, but for this compactly supported, narrow signal, you're going to shift it. And having said that, you look at these two different classes. I mean, this here obviously not a smooth signal, there's discontinuities, and this is a smooth signal. So the impact of this nonlinear deformation here is, you would agree, quote unquote, much less than it is here, because here it ends up in a signal that is completely different. Having said that, that means that we may want to ask for deformation in sensitivity with respect to signal classes. And that's what we have been doing, and that's also how you can view Malaz results. So here is again a comparison. Again, you look at the error induced by this nonlinear deformation in the phi w, so Malaz wavelet scattering network. And here's the upper bound that he gets, and this is the upper bound that we have here. So let me interpret these two bounds. Our bound here applies to explicit signal classes. Those could be band-limited functions, could be cartoon functions like David introduced in 2001, or could be Lipschitz functions, or actually there's a much broader class of functions that satisfy some kind of inherent deformation in sensitivity. And the upper bound depends on the size of tau in a certain way. And here the upper bound depends on the number of wavelet scales and on the first and the second derivative of tau. And it turns out, if you read carefully in Malaz's paper, the signal class HW that he looks at, so he says for all f in HW, this bound holds, this signal class is, it's implicitly characterized. It depends on the mother wavelet, and it depends, of course, also on the modulus nonlinearity, but it's an implicit characterization. Here the signal classes are explicit, if you like. Now, the constant that we get here depends on sort of the description complexity of the signal class. So if you have band-limited functions, then it depends on the bandwidth. If you have cartoon functions, there is a concept of size of a cartoon function. It depends on the size of the cartoon function. Or if you have M-Lipschitz functions, it depends on the Lipschitz constant. And the exponent here, alpha, so this is of course the sup norm. The exponent is 1 for band-limited functions, 1/2 for cartoon functions, and 1 for Lipschitz functions. Okay, so the way to summarize, I like to compare these results is, this is an implicit characterization of a signal class that depends on the mother wavelet and hence the network, and these are explicit characterizations. Malaz bound depends on higher order derivatives of tau explicitly. Here there is an implicit dependence. Our bound applies only to taus that satisfy this condition here. So the sup norm of the derivative is less or equal than 1/2d. So that's how we impose limits on the size of tau, not any tau is allowed. And it turns out that the bound in Malaz's work is coupled to horizontal translation variance. If you let j go to infinity to get translation variance, horizontal, meaning in every layer, as compared to, in our case, only in deeper layers, then you need to let j go to infinity. Now looking at this here, the first term is fine, but you see here that this term actually goes to infinity. Okay, so that's a coupling. We call it coupling of these two bounds, whereas here it's decoupled. Okay, but it's for explicit signal classes. So these are the two different philosophies. Good. Now I want to switch gears, and I would like to talk a little bit about the topology of deep neural networks. And I want to ask the question, so there's one aspect that is still missing. So I think I told you that we need nonlinearities to get translation variance. I told you you need depths to get translation variance. Because if you don't pool and you go deeper and deeper into the network, you don't get translation variance. The question is now, what about locality of features, the Fourier transform versus more localized transforms? And what about the size of the network? How big do these networks have to be? And if you read about recent successes of deep neural networks, I mean, you read numbers like this here: 2015 ImageNet contest, 152 layers, 472 nodes per layer, number of flops in a single forward pass, 11.3 billion, and so on. So these are big numbers, and training and operating those networks, of course, more training, but also operating those networks is quite challenging. At this point, I would like to make a disclaimer. I'm sure you noticed in our series so far the frame condition. This is for all L2 functions. So having said that, we need infinitely many filters in each layer. So that's of course not something you can do in practice. So if you're interested in how wide these networks have to be, I won't have time to talk about that, but there is a paper where we essentially say we look at input signals that are Sobolev, so they're decaying, they're effectively band limited, and then you can say something about how wide these networks have to be. But technically and formally, in what I'm doing here, we have infinitely many nodes in each layer, and that's simply because the theory is easier to present that way. But anyways, what we want to ask here is how deep do those networks have to be? And the question is in particular, do we have to have 10,000s of nodes? And the question is also, how do we ask that question? I mean, how do we formulate this in a meaningful way? And what are the constraints that we impose? Now, what we want to do is we want to do we want to look at the energy decay in the network, and the feature maps that are generated in each layer. We want to measure how much energy there is, and if the network is to perform well with a small number of layers, somehow the energy in the feature maps should decay, meaning that the deeper you go into the network, the less energy you should have there, and the less relevant eventually the features should become. We want to do that while guaranteeing a trivial null space for the feature extractor, and I'm going to tell you in a second what happens if you don't have that. And then we want to quantify the number of layers needed to have most of the input signal energy be contained in the feature vector. So how deep do you have to go if you say, I want to pick up 95% of the input signal energy? And eventually we want to see if we can design networks that are actually shallow and capture most of the input signal energy. Okay, good. Building block as before, however, there's an important difference. The pooling we look at now is subsampling, and the nonlinearity is the modulus. The filters are still general, and in particular, the filters can be different across different layers, okay? But what remains constant and fixed is the modulus nonlinearity. We need the frame condition. Now, the pooling operation, you can actually do averaging also and so on. I mean, it's just a bit more difficult to expose here. That's not a big deal. But the modulus, you will see actually, I'm not sure whether we can get energy decay for more general nonlinearities, and you will see why there's some numerical results.
Yes. So one of these students actually had a question about max pooling, and he said, when you say subsampling, does that include max pooling too or not? So
yes,
maybe you can
it's a good question. So the continuous time theory I'm presenting here does not include max pooling. However, there is a discrete version of this theory that you can find it on my webpage. There's a paper that includes max pooling. But in the continuous time theory, there's technicalities that don't allow us to deal with max pooling. Good. All right. Anything else for now, or?
Yeah.
Good. Go ahead. Yes.
Yeah, so for the first part of the talk, you talk about that you have two signals and translation learn from each other. You have an upper bound for the feature vectors. You have a similar result for a lower bound. So if you have two pictures,
No.
one translation learn.
Yes, so the question was for translation variance, we had this upper bound that was O of magnitude of the translation divided by the product of the S's. Question was, is there a corresponding lower bound? The answer is no, we don't have one. Good. Anything else for now? All right, so then let's move on. Okay, here comes the locality aspect. I told you in the beginning, Fourier transform and modulus, this gives you translation variance, but it's not a local transform. Now, we look at an example, Weil-Heisenberg filters. What does Weil-Heisenberg mean? You take a filter and you shift it in frequency to get the other filters. So these are ideal bandpass filters, if you like. This is what is called the output generating atom, or the low-pass filter that extracts the feature maps into the feature vector. And these are the different filters that we have here. So suppose you pick out this part here of the signal, then you get this here. Now let's try to understand what the modulus does. And in order to understand that, we first look at the modulus squared. What does the modulus squared operation correspond to in the frequency domain? Well, in the time domain, it's f of t times f star of t. Now in the frequency domain, the multiplication becomes a convolution, and f star becomes f star of minus. So you convolve f of f hat of w by f hat of minus w star, and that gives you the autocorrelation function, okay, the magnitude squared. All right, so what does the autocorrelation, when you autocorrelate this signal here, what happens is that you shift it to the origin, okay, no matter where the signal is located. Okay, so it's going to look like this, and then the output generating atom is going to extract it. But now you will say, hold on, we actually are dealing with the modulus and not with the modulus squared. You can't just throw in the modulus squared. Well, I'll show you in a second why it's still possible. But first, let's ask the question of whether all nonlinearities demodulate. So the modulus does, I will show you, but others may not. So what happens is, if you replace the modulus squared, which perfectly demodulates, by the modulus, you see actually that it acts almost like the modulus squared, but it has these small, decays, and then there's some part of the signal is left here, okay? But that's what the modulus does. And there's actually some theory you can do. There's some about square roots of convolutions and so on. So this actually, you can show that this happens for the modulus. Yes?
So one of these students wants to know, can you clarify the difference between G of lambda and psi that you use?
Right. So you have an overall set. This is a frame. You designate one of the filters as the output generating atom. In this example, it's a low-pass filter. And all the other filters act as feature map extractors. And this designated filter does the following. You take the feature maps, which are convolutions of the input with the filters, modulus or whatever nonlinearity you have, and then you apply that filter to that. So it extracts the feature maps into the feature vector.
So the psi here is basically the low pass.
Here it's a low pass in this example, but it need not be. Okay?
Thanks.
Good. All right, so modulus demodulates. Modulus squared does, and sharply so, because it autocorrelates. So what happens with the rectified linear unit? Looks like this here, okay? And that is an issue. Why? Well, if you go back to this picture here, if you're interested in energy decay, the way you can think about this is the following. You take any of these filters here, you demodulate to the origin, the low-pass filter extracts this into the feature vector. What remains is actually the information here outside, and that is fed to the next layer. And in the next layer, you see that the filters will act upon this, but only the next one is going to extract something here, and those are going to extract 0. And so then, of course, the bandwidth here is smaller. The autocorrelation doubles the bandwidth, and then in the next layer, you get the idea. Pull out the whole thing here, and there's going to be nothing left outside, and the energy decays, okay? And it turns out that you can analytically show that if you impose analyticity conditions on the filters, the frame condition, together with the modulus nonlinearity, you get actually exponential energy decay in the network, all right? But for the rectified linear unit, because of this here, I don't know. So that's something that, I'm not sure it happens at all. Certainly we cannot prove anything about it at this point. Okay, so we want to quantify the feature map energy decay. Feature map energy decay is in each layer. You have these feature maps. You just compute the overall energy, and you do that for every layer, and you try to see how fast the energy decays. And remember, the idea is that you do this in the first layer, you extract this, and in the next layer, you have a filter here, here, and so on, pulls out this one, shifts it to the origin, pulls it out, nothing left, more or less, okay? Good, but you do need this interplay between the autocorrelation, the demodulation property back to the origin, and extraction via low-pass filtering. However, it turns out that you can get energy decay for general frames. You designate one of the filters as the output generating atom, and together they have to satisfy the frame condition, and the modulus nonlinearity has to be used. So this is the analyticity conditions of the filters. So the output generating atom has to be concentrated around the origin, because you demodulate with modulus nonlinearity. And the filters have to be analytic, and I don't want to go into details, just think of it in 1D. Each filter's Fourier transform has to be supported either in the positive or in the negative frequencies with some distance from the origin, okay? So some kind of analyticity condition. The input signals we are going to look at are Sobolev type. So Sobolev class signals contain square integrable functions, that's Sobolev order 0. They contain L band limited functions, and they contain cartoon functions as introduced by David that, for example, would be a good model for handwritten digits here, and the Sobolev parameter would be between 0 and 1/2. Okay, so that's, and why are we going to work with Sobolev functions? Well, it's a fairly general set of functions, and it's going to allow us to get analytical and explicit results. Okay, now here is the main result on energy decay. if your filters are either wavelets or Weil-Heisenberg or Gabor filters, so this would be an example, a filter that is located, or spectral support is between -RR, and then you shift, and then here's a wavelet, and then of course you scale. I'm going to show you a picture later. Then what happens is that the feature map energy decay is exponential, and there is a decay coefficient that depends on the bandwidth of the mother wavelet, and the decay coefficient depends on the bandwidth of the mother Weil-Heisenberg filter, and the Sobolev order shows up in the exponent here, and a beta parameter that essentially tells you that depends on each signal f, so this beta depends on f, how fast the signal decays. So just think of Sobolev functions as functions that are effectively band limited. Okay, so that means you get exponential energy decay. That's pretty fast. If you ask, well, how much does this result depend on the structure of those filters, be it Weil-Heisenberg or wavelet? So this is the the affine group is the coherent or Weil-Heisenberg group, then the answer is, well, not really on the structure, but it depends on how the spectral support of the filters behaves. Here the spectral support is constant. Here it scales because you do the scaling by computing the different wavelets. These are two extreme cases. In one case the spectral support remains constant, in the other case kind of expands. Anything in between actually you can show work, so you don't have to have the affine structure or the Weil-Heisenberg structure. It's just a condition of the spectral support, and has nothing to do with the affine group or the Weil-Heisenberg group. Okay. This will turn out later to be important. You can tune the decay coefficient through the bandwidth of the filters. Now, here is the decay condition, Sobolev condition, effectively band limited, and what the result also nicely shows is that the smoother the input signals, meaning the larger your S is, the faster your energy decay. If you do pooling through subsampling, you still get exponential energy decay, but the decay coefficient turns out to be A divided by S, so the decay is going to be slower, or with a different coefficient. Now, if you have very general filters, no condition on the spectral support, you get polynomial energy decay, but that's a case that, of course it's good to know that you still get energy decay, but polynomial is actually not something you will be interested in too much in practice. Okay, the second goal, we want to get all this while ensuring a trivial null space. Why would we want to have a trivial null space? Let's suppose you have a dichotomy of points, blue and red, and you want to linearly separate them, and you've already mapped them into feature space through a deep network, for example. Now, what happens to those filters? So essentially, you separate them by computing the inner product of your feature vector corresponding to f with your w. What happens to those points, f, that lie in the null space of this operator? And remember, this operator phi is a nonlinear operator, so characterizing its null space is not just looking at eigenvectors and so on. Yes, please.
For exponential energy decay, other than intuition, do you have any results saying why we would necessarily want this?
Yeah, I'll show you some numerical results, because if you have exponential energy decay, that means that the network can be relatively shallow, and you're going to absorb most of the input signal energy in the first few layers, and I'm going to quantify that later. So it's a practical question of how deep does the network have to be. Okay. Good. Okay, so what happens to vectors f that are mapped to 0? Well, obviously, if there is an f star that is not equal to 0, that is mapped to 0, this is going to end up here in the origin, and it's going to become unclassifiable. So all the signals that lie in the null space of the feature extractor are going to end up being unclassifiable, and that's not something we want. So we want to ensure that we have a trivial null space. And indeed, you can show that you get a trivial null space for analytic filters paired with the modulus nonlinearity. What is more is you get this double inequality. So your feature extractor satisfies this lower bound and an upper bound. Looks like a frame condition, but mind you, this is a nonlinear operator. And it's this lower bound that guarantees that obviously the only way for this to become equal to 0 is for f to be equal to 0, because if f is not equal to 0, then the lower bound is positive. Okay? So that is guaranteed, and that's actually where most of the juice in the proof goes into in establishing this lower bound here. The upper bound is fairly simple to do. And the lower bound really explicitly uses the interplay between analyticity of the filters and the modulus nonlinearity. Okay, and also we get, this the frame bounds of the filters in each layer. They show up as the multipliers here in this quantity. By the way, for those of you who have looked at generalization and so on, the radius of the feature extractor, the size of this radius, this shows up in the Wapnick-Chevonenki theory and so on. So you want to have some control of that radius, and it's good to know what this B is going to be. Okay, if you have Parseval frames, tight frames with frame bounds equal to 1 in every layer, then you get perfect energy conservation. And now that allows us to look a little bit into the interplay between energy decay and the Parseval identity. Namely, what you can show is that the overall input signal energy is equal to the energy in the feature vector corresponding to the first n layers plus the energy in the feature maps. So the feature vector is obtained from the feature maps by filtering by Xi. Okay, that means if this is to be satisfied, meaning that as n goes to infinity, this quantity becomes equal to that quantity, this has to go to 0. And how fast it goes to 0, we just showed it's exponential, or in the worst case, it's polynomial. Okay, the third goal is now number of layers. This goes back to your question here. How many layers do we need to specify to capture most of the input signal energy? So what we do is we just look at this lower bound here and we say, well, we want to make sure we are not interested in perfectly satisfying this frame condition. We want to make sure that the first n or n plus 1 layers contain at least 1 minus epsilon of the input signal energy. And again, we look at Parseval frames because we know ideally this would be a Parseval condition. And so you pick your epsilon point 1%, 5%, 10%, whatever. And here's an analytical result that tells you the number of layers has to be larger or equal than this quantity here. It's for band limited functions. You can do it for Sobolev, but for simplicity, I just put it for band limited. And what does it tell us? Well, it depends on the bandwidth, it depends on the decay coefficient, and it depends on your epsilon. And this also guarantees a non-trivial, a trivial null space for the feature extractor corresponding to the first n layers. So the trivial null space is not an asymptotic property in the sense that things could get lost in the first layers and they pop up in the later layers. No, it's actually you have to have it throughout. Okay, good. Description complexity, bandwidth larger makes the number of layers larger. The input signal is more complex. And this I'm going to show you a picture in a second, how the decay factor impacts that result. Here are some numerical results. If you look at a band-limited signal with bandwidth 1 and you have different epsilons, 1%, 5%, 10%, 25%, you have a wavelet-based network or a Weyl-Heisenberg-based network, this is the number of layers you need. So for example, if you want to pick up 99% of the input signal energy, you can do with 11 or 14 layers. If you want to pick up 95%, you can do with 8 or 10 layers. If you contrast this with the networks used in the ImageNet contest, this is quite a difference. And of course, why would you want to have shallower networks? Well, because they are easier to train and easier to operate. I mean, 10 layers are easier to train and operate than 152 layers. What I kind of didn't show you here is that there is a width aspect. And I said before that technically we have infinitely many filters in each layer, so we have infinitely wide networks. But you can actually, because we have Sobolev functions, you can actually see that there is a depth-width trade-off, and it really turns out that networks that are shallower, they are wider, and there is a sweet spot. So there is an optimum choice for this bandwidth of your mother wavelet and your Weyl-Heisenberg generating filter, so as to minimize the total number of nodes in the network. And as I said, that's something I don't have time to show you here, but there's a paper, you can look it up. And what we do here now is the last point, we want to ask the question, is it possible to design a network of a certain number of layers, let's say 3 or 4 or 5 or whatever, to make sure that I pick up 1 minus epsilon of the input signal energy? And the answer is yes. With this Weyl-Heisenberg or wavelet network, we can do that as long as your bandwidth for the mother wavelet or for the Weyl-Heisenberg filter satisfies this condition. Anything in between is fine, and then you're guaranteed to have 1 minus epsilon fraction of the input signal energy in the first capital N layers, and you can have quite shallow networks. However, what happens is that if you want your network to be shallower, smaller depths, N, then you need a smaller bandwidth of your mother wavelet. So in each layer, you need more filters to kind of pick out, the signal is Sobolev, but to still pick out most of the input signal energy. Yes, Manuel?
I'm just picking up on something you said, which is you said that you want shallower because it's faster to train, but you're not, if I understand correctly, you're not training anything.
No, here we are not training anything.
Right.
Yeah.
So that's my question. Like you said, I want to
Yeah.
shallow network because I don't want to train.
Right.
At the same time, you present a view of the world where
Right.
you're not training.
Right.
And so
Yeah, so-
perhaps that's a part that I'm not.
Okay, good. That's a very good question. So what I can say about this is the following. The conditions I gave here is that these are filters, Weyl-Heisenberg or wavelet, where you just specify the bandwidth and the shape is irrelevant, okay? And then you can go ahead and you can say, well, in practice, different shapes give you very different performance, and then you would train for this shape. And that's where the training comes into play.
That's where the training comes in.
Yes.
And then you're going to try to find the filters
By whatever
by some method.
algorithm you have at your disposal.
But then, and then they will be subject to this kind of Parseval condition, or
Yeah. Parseval or frame condition in general, which, as you know, is fairly easy to satisfy. I mean, you just avoid the common zeros, okay?
The way you see the workflow is I'm going to train this filter subject to this condition.
Right, exactly, right, okay. So there's a lot of freedom. Yes,
If you
yes.
could just summarize this exchange for the
Yeah, okay,
people
good.
who have to listen through the microphone.
All right, good. So Professor Kantas asked a question of training, and I said that I keep talking about predefined filters, and now I say I want shallower networks because I want to make the training effort small. And the response I gave was that you just specify the bandwidth of the filters, but within that bandwidth, the shape of the filter can be anything subject to the frame condition, and clearly different shapes will give you different performances in practice, and you would then train for the shape, but you want to make sure that the number of filters in the network, the depth and the width, is small enough so as to make sure that your training effort is not extraordinary, and later, of course, the filtering effort when you operate the network. Good. Okay, so anyways, here is the trade-off. There is a depth-width trade-off. If your bandwidth of your mother wavelet has to be smaller and you have Sobolev functions and this decays in frequency, you want to pick out most of the input signal energy, then you need more filters if your bandwidth, your R is smaller, and you get this depth-width trade-off. And as I said, if you're interested in the details, there's different networks. We call them constant width networks, that actually you can show that almost no signal energy is outside a certain number of filters that you have, or then we have networks that behave like this, you get the idea, networks that behave like that, and so on. So there's all sorts of, it's just some bookkeeping and so on, but you can ask the question, in some cases you can get analytical responses, how can I minimize the total number of nodes in the network if I give you the epsilon? I want 5%, so 95% of the input signal energy, and I want the shallow network, and how can I minimize the total number of nodes? Do I have to go deeper or wider, and so on? And so there are results on that, but I think I'm over time already. So with that, I would like to thank you and open the floor for further questions.
So I'm going to go over the questions that students asked during your talk. Alex is asking,
It's just recording, but it's not a room mic.
So he's asking, does the concept that you told us extend beyond the scattering network? That's his first question. And then he's saying, how do your results change if you include the bias term that they have in deep nets? They use a bias term. Would that change your results? And then is there a hope that we could basically analyze dropout and batch normalization in your framework?
Yeah, okay, that's a very good question. So there's two parts, and let me first answer the part that is not on the bias term. Okay, so bias term is, you have a filter plus some constant. Okay, so I'm going to answer the first part. So first of all, the network architecture. So ResNets are included, dropout, then there's shortcut connections. All these things you can actually include in that theory. It's just that in continuous time, some aspects of the theory get to be more beautiful, but other aspects are more difficult to present, and then those are the general architectural aspects. So if you're interested in seeing how these different architectures that are used in practice, like ResNets, dropout, and so on, and batch normalization I will respond to separately, are included. I want to refer you to the discrete version of this paper, which is published last year. You can find it on my webpage. If you don't, please let me know. But yes, I said this in the beginning, then I forgot to comment on it. So that's a good question.
Yeah, I'll just comment. I believe that at the Canvas site in Files, lcskei, there's a whole ton of papers, all the archive publications that he's probably referring to.
Right.
And on the GitHub website, there are links to a variety of the readings associated with this lecture.
All right, thank you. So batch normalization, essentially, we looked at the energy decay. And so when you say batch normalization, what people do is they kind of normalize the energy in different layers. And you can do that. The theory allows you to apply these normalizations. In fact, the way I like to view this is that the overall network is Lipschitz. I didn't talk about that, but the overall feature extractor is Lipschitz, and up to any layer depths, and also as you let the number of layers go to infinity, it's Lipschitz. And then we have this admissibility condition that is easily satisfied by normalizing those filters here. So you can play with the Bn here. And interestingly, doing batch normalization, normalizing the filters, is not going to impact the translation variance and the deformation sensitivity. And I think that answers that question. You can normalize invariance, and deformation sensitivity will actually still hold. Okay, and
the bias question.
And the bias question is a good one. I haven't spent much time thinking about it, so I would prefer to not cook up something and just leave it with, well, certainly I thought about it, but I couldn't find anything mathematically appealing and so on to say on this.
So, AJ is asking, a significant idea from the first two discussions in this class has been the relative absence of theory in the face of brute force in deep learning. Is this a notion you would agree with? Why or why not?
The relative absence of theory. Well, I guess it depends on how you define a theory, and I think we talked about this over lunch. Different people think that understanding something means something very different, and different people think having a theory for something very different. The way I would like to phrase this, and I think this is a general attitude which we also talked about, is that I don't think these things should be viewed in a with absolute mindsets and so on. I would say that the fact that not much mathematics, deep mathematics had been done is something that should encourage and invite people. And I think it's impressive what has been accomplished. And I think the universality aspect of these networks is what I find most remarkable, that the same super architecture works so well for very different applications. Speech recognition, speech translation, ImageNet, MNIST, whatever you have it. It's one architecture, more or less, that works well for all of those. And so I think it's whatever you can find to explain this universality is useful and interesting. And I think it's rather a feature and a chance to do some theory. And I would not qualify this. When I read these practical deep learning papers, I'm deeply impressed by the intuition that people have and what they can do without having the mathematical walking stick helping them along, like many of us are used to. So I think that's remarkable. That's like, I would say, there's some mountaineers that can free solo, and there's others that need ropes to support them.
Okay. Well, so Ken is asking, how should I understand your figures? Are you suggesting that the winners of ImageNet were doing something suboptimal since it was using many more layers than that needed for wavelets or WH filters?
Well, I think, again, it depends on what you think, what you consider optimal. But yeah, what I'm saying is that if you're interested in extracting most of the features, and I talked about energy, amount of energy, but clearly if you extract 99% of the input signal energy, you are bound to have most of the relevant features in your signal. And then these results tell you, yes, you can do it with 152 layers, but you technically could also do it with 10 layers. But then the practical aspect comes into play. Maybe these shallower networks that I'm apparently implicitly advocating, maybe they're much harder to train, and maybe the cost functions become much more benign if you go deeper into the network and so on. That's an aspect that I completely ignored. So I would not answer this question as saying that they did something suboptimal. They did whatever worked for them in practice.
Yeah. Maybe the last 5 minutes, maybe we spend on audience, but let me go through the people who have actually, put questions on Canvas. So you mentioned random convolution filters give good performance in your talk, but in actuality, convolutional kernel weights are learned over time. So can you clarify what do you mean by random filters working well?
Right, so there is a number of papers, I'd be happy to give you the references, that even look at picking those filters as realizations of random processes and then operating the network, and they do quite well actually. And there are other papers that learn those filters and they also do quite well. But the interesting thing is, kind of my reading of this is that if you draw them randomly, so you don't care of what they are, if you go deep enough, you still get reasonable performance. And I think that's remarkable about the architecture, and that's really literally what people have been doing, drawing random filters and going deep enough and operating the network and saying, look, we get invariance, we get deformation sensitivity, and many other desirable properties.
Okay, with this, maybe we can get maybe 2-3 questions from audience. So yeah, I'll give it to you so maybe you can ask.
So you presented this framework, and so we assume, for example, we have the translation invariance and deformation insensitivity. But can you actually prove that these features have discriminant power? So if I have two classes, I can come up with very intuitive things. I can multiply everything by 0. Mm-hmm. That would give me translation invariance and insensitivity. Right. But all my classes would be mushed together, basically.
Yes, so first of all, analytically, stay tuned and please check our webpage. So I think that's actually the big thing that I think is interesting, to look at the structure of the separating surfaces of these networks. And there's different ways of looking at this. You can let the dimension grow large and look at strong converses or phase transitions and so on. So that's I think an interesting viewpoint. You can try to, Tom Kober has a beautiful paper from I think 1965 on the separating capacity of general networks with nonlinearities. You can take that viewpoint and so on. So that's missing in that theory, and that's something we currently work at. So analytically, we have nothing published yet, but numerically, there is experiments that we did comparing to the state of the art with a very simple network, because these things get computationally out of hand very quickly. So what we did here is we looked at a wavelet-based network. So there's this result by Brunat and Malat for handwritten digit classification, and they have the state of the art is 0.43% classification error, and they have directional non-separable wavelets and no pooling. And so we looked at this with separable wavelets and with pooling, and the computational complexity of this network that we looked at is quite a bit lower. We get a little bit of higher error rate, 0.51 and 0.52, And these are very close. I mean, if you go to, I think Jan LeCun operates the web page. If you go there, you see 0.36, 0.37 is kind of the state of the art and so on. So, I mean, numerically, we have done also other experiments. These things work quite well. So they must have separating capacity. But to prove this analytically, I think there's a whole universe out there, and that's certainly for further work.
Another question. If I understand correctly, the scattering network and everything you've shown assumes that all the filters throughout all the layers are always two-dimensional and not three-dimensional like in current CNNs. So first question is this correct? And second question, if it is correct, what's your opinion on this?
So the theory that we presented here is for RD. So D can be anything.
But the filters that you're convolving, the wavelets,
yes.
What dimension are they?
The pictures I showed were for D is equal to 2, but the theory applies to any D.
So if you go back to the...
Let me just clarify. I think what he may mean is, for example, if I have RGB data, like in other words,
right.
the range space of the underlying object is not like R1.
Oh, I see. But something else.
You have another feature space. That's part of
right.
it. And then there's some other aspects he's getting at.
Also in CNNs, for instance, if you look at the number of channels in each three-dimensional volume, so it's usually like, let's say 64, 128 to 56, etc. But here on the other hand, each time you take some channel and you convolve it with a bunch of wavelets. So let's assume you have, I don't know, 64 wavelets. So the first layer would have 64, the second would have 64 squared, the third would have 64 to the power of 3, and then you're dead because of gravitational hazard. So is this correct?
Yeah. So let me first try to respond to the first question now that I understand it better. So yes, we have filters that map RD to R, actually R. Can you be more general? Can you use operators, essentially, mapping RD to RK or whatever? I believe yes, and many things should go through. I mean, there's this G-frame concepts and so on, but I cannot respond to this firmly. So I would be quite confident that things will work out. But yes, the current theory is RD mapping to R. Okay, so that's what it is. And the second question is, there is a paper by Radu Balan who looks at these types of networks, and he aggregates in each layer through linear combinations. So he has these wide matrices, and you have 64 squared, and then he brings it down to dimensionality, and he looks at the spectral properties of these aggregating matrices, and then he comes up with conditions for translation variance deformation sensitivity to still hold. And the idea is to make sure that the network doesn't go out of hand and that you contain its size essentially. And it's again interesting how robust translation variance and deformation sensitivity are, even if you aggressively aggregate in each layer.
And if I can have another question.
Maybe in the interest of time. We'll
Sure.
So audience can ask one more question, and then if there is any other question that you would like to ask. Okay.
So in the scatter network and in this network architecture, the main focus is to prove like some reconstruction or some preserve some norm of the operator. So I'm wondering, when people doing prediction, why do we want to keep all the information? Since there are other group of people who have this information bottleneck theory, which says we want to forget irrelevant information and keep all the only the relevant features that is useful for prediction for certain tasks.
Yes. So, yes, I agree. I mean, this is obviously, so if I wanted to respond, to tweak things and respond in a favorable, I mean, from my perspective, favorable way, I would say, if you pick up 99% of the input signal energy, you have picked up all the features you essentially are interested in. So it's you don't need structural information, and it's a robust or a universal result, if you like. But I agree with you, if you want to go and impose more structure, in particular in the case of prediction and so on, so then this kind of L2 type of theory, with frames and lower and upper bounds, it's all L2, Euclidean and so on. Not so sure. I mean, you would maybe, can these structures be described through subspaces? Then you could probably do things. If you have more sophisticated structures, I doubt that the theory just, flows through. So I think there are limitations in this, clearly.
Dave, do you have to come?
So I have a question and then an announcement. So one thing that I showed last week is there's a a rhetorical device that's very important to practitioners who have a neuroscience leaning, which is that the features that get trained in existing empirical efforts, at the finest level, yes, they do look like Gabor or like wavelets, but then as you go to higher and higher levels, you start to see new kinds of features which are sort of parts of objects and then whole objects and so on. Is there a sense in which that's reflected in your approach, or do you have any comments on that that common rhetorical stance? People like to show that that deep nets make sense.
So there's this features of features kind of thing. That was one of the reasons why we wanted to have a theory that applies to networks that have different filters in different layers. So we index the layers by n. So that means that you can pick a Gabor system in the first layer, wavelet in the second, and shearlets and ridgelets and whatever and so on. So the theory kind of contains that, and it says that as long as these filters satisfy the frame condition, no matter what their structure, you're going to get invariance and deformation in sensitivity. And the second is training. I mean, that's something you see experimentally, and we have not looked at this, in a large enough scale, to confirm. Or no, this was not something that we really looked at. But I am aware of these things, and I think the main thing is the theory does apply to general filters and different filters in different layers.
Okay, so I have an announcement, which is we have a change in the speaker schedule. So Bruno Olshausen, because of a grant program review that he has to do next week on October 18th, we've moved him to November, I think, 29th. And October 18th we'll have a speaker from Rice University, Ankit Patel, who's going to speak about the paper, A Probabilistic Theory of Deep Learning, which is joint work with Rich Baraniuk and others at Rice. So we have a change in speaker next week, and the reading list is updated. And meanwhile, I would like to comment that I thought this was exceptionally well delivered and interesting talk, and I would really like to thank Helmut Bolske for traveling all this way to speak to our interested group of Stanford students. Thank you so much.
Yeah, thank you.